So the last lecture we have seen the standard formulae and the equations used in projectile motion. Take it ahead from that point onwards today. Okay, so this is session number 5 of kinematics. Let's take it from where we left in the previous lecture. So quick recap of the standard equations and the important formulae related to the standard case of projectile motion. The standard case being when we project an object from a horizontal plane and that object returns back to the same horizontal plane. That is the standard case of projectile motion. So we project something at time t equal to 0 with a projection velocity u, which is at an angle theta with respect to the horizontal. Then it goes in this kind of parabolic path as we saw. And it returns back to the ground with the same speed u at a symmetrical angle theta like this at the time capital T. And in between, it ascends and reaches a maximum height of h at the time t by 2. At that point of time, its velocity becomes horizontal and u cos theta. And also this horizontal range is r. So the important equations here was if we take vertical and horizontal axis like this, and the origin at the position where you release the particle, then we've seen the equations of motion such that at any time t, the position and velocity are given by this kind of relation. X coordinate is horizontal velocity into time, whereas the y coordinate is u sine theta t minus half gt square. And the velocity vector is such that the horizontal component is constant and the vertical component is having a uniform acceleration of minus g. This is the case. Okay. And from these equations only we derived the standard formula that time of flight is 2u sine theta divided by g, or 2 times uy divided by g. Initial velocity is y component, that is, okay. Maximum height is u square sine square theta by 2g, or uy square by 2g. And the horizontal range was given by the formula u square sine 2 theta divided by g, or we can understand it as the horizontal component of velocity multiplied by time of flight. Okay, so this set of equations and formulae almost contains everything that we require to solve questions related to the standard case of projectile motion. Okay. However, there was also something called equation of trajectory, which we will discuss next. And today we will start by understanding the application of equation of trajectory in certain types of questions. Okay, so let's start with a quick numerical problem. An object is projected Okay, so the second question is the interesting part in this particular example. The second part is that we have to find the time, because the particle is projected with this velocity with respect to the horizontal at p equal to 0. Okay. Now we have to find the time at which its velocity vector is making an angle of 45 degrees with respect to the horizontal. Okay, Kirti, I will verify your answer. Okay, just continue with the next part. Okay, Anirudh, that's correct. Preeti, your value of time of flight is correct. Check your answer for range once more, but okay.
Yes, sir.
Maximum height is also correct. Good. Anirudh, your answers are correct, all three parts. Okay, so if we're taking this as a y-axis, the vertical, and the horizontal as our x-axis, as you do. Then at t equal to 0, projected it at 60 meters per second, then this angle is 53 degrees. So it will go in this kind of a path. I mean, hit the ground again. Okay. So while it is going in this kind of path, it will reach some position here, let's say, where at some time t1, the velocity is v1 such that this angle is 45 degrees. Okay. Then of course it will reach the highest point where the velocity will become horizontal. And then again on its way down at some symmetrical point, it will have a velocity v2. So this angle is again 45 degrees. You see that these two times t1 and t2 are also related because of the symmetry. And eventually it will come back and hit the ground. So at the instant when it hits the ground, the impact speed will again become 60 meters per second, but this angle will become 53 degrees. Okay. And will be capital T. So we can see here that the initial velocity is 60 cos 53. So that will become 36 I cap plus sine. So 48 J cap. That is whereas the acceleration is minus 10 J cap. So this is the first set of data that you use. Okay. So the first question start with time of flight.
Sir,
Yes.
sir, u by has to be u sin theta minus dt, no?
That is Vy beta. Velocity as a function of time. Initial velocity. The initial velocity is y component is how much?
Okay,
Is
okay.
u sin theta. Understood? No? Okay. So yeah, so that will also come into the picture when we do the second part where the angle has become 45. Okay. So anyhow, so in the first part, the time of flight therefore becomes 2 into 48 divided by 10, or it becomes 9.6 seconds. Then the maximum height u square sine square theta by 2g, or uy square by 2g. You can write it like that also. So that is going to be equal to uy is 48. So this maximum height will come out to be, when we calculate it, just a second, let me verify the calculation. So 115.2 meters. Now, when it comes to range, I can use this formula, or I can understand it as the horizontal velocity to time of flight, which will be somewhat easier actually. So by this explanation, it is equal to horizontal component of velocity was 36, okay, and the time is 9.6 seconds. So the range will become okay. So that is the standard set of equations. Okay. Now for the second part, I mean standard set of formulae. Okay. Now for the second part, we have to find, for example, in the diagram at t equal to t1, the velocity v1 will become how much? It will become u cos theta I cap plus u sin theta minus gt1 j cap. Now, if this is at 45 degrees with respect to x-axis, it means that, so numerically this is 36 I cap plus 48 minus 10t j cap. Now you can see that if this velocity vector v1 is making an angle of 45 degrees with the horizontal axis, then its x component and y component should be related such that they are equal in magnitude. Okay. So this implies that tan 45 is Vy by Vx. So this is the time. But there's also another time t2 at which this happens, okay, which I've shown in the diagram. So the answer to the second part is there are two instants of time. One is t1, which is 1.2 seconds, and the other is t2, which we will see will be 8.4 seconds. When again the velocity will be at 45 degrees to the horizontal. So make sure you're understanding this second question, second part very carefully.
Sir, how do you get u cos theta 36 because theta is 45?
No, u cos theta is constant, beta. Theta is not the angle 45 over here. Theta is the projection angle 53 degrees. You understanding, no?
Okay.
Whereas at that instant of time t1, the angle with the horizontal is changed from the original value 53 to 45. While it is ascending, that angle is decreasing from 53 degrees originally to 0. Then while descending again, that angle is changing.
So if it was 30 degrees, so tan 30 would have taken.
Yeah, any angle it would have been there. Okay. So the angle will reduce from 53 to 0 in that time 0 to t by 2. So it could be any angle less than 53 at any instant. Now the second thing is, you can see that at t equal to t2, the velocity vector is 36 I cap plus 48 minus 10 t2 j cap. Now this should be symmetrical. No? This should become 36 I cap minus 36 j cap. Because now that velocity vector is like this. This is your v2 and this angle is 45 degrees. So remember, in projectile motion, the horizontal component remains constant. So it is the vertical component which is changing in such a way that in this case, the vertical component should become minus of 36, so that this angle is 45. So that's how I got this. Okay. So from this, we can see that 48 minus 10 T2 should be minus 36. So T2 will come out to be 8.4 seconds. So there are two instants when this is happening, that the velocity vector is making an angle of 45 degrees with the horizontal. Once when it's 45 degrees above the horizontal, that's T1, 1.2 seconds. And then again, once on the way down at 45 degrees below the horizontal, below the x-axis like this. Okay. And that's at T2 equal to 8.4. And you can also understand by symmetry, T1 plus T2 is equal to capital T because they are symmetric situations. They're two symmetric positions. Okay. Magnitude of V1 is equal to magnitude of V2. Yes, very good, Anirudh. That's correct for the third part. Yes, Rohan, to find T2, we just using the same type of concept that you look at the vector diagram over here, which I've drawn for V2. You can see that if this angle is 45, the vertical component has to become minus 36, no? So that this angle is 45. So tan 45 is the magnitude of this vertical component divided by the horizontal. Okay. So Vy is becoming minus 36, you can see here. So the general expression for y component of velocity is what? It is u sine theta minus gt, which is this value here, 48 minus 10t. So this 48 minus 10t at that instant should have become minus 36. So from that we are solving for the time, it's coming out to be 8.5 seconds. Is it clear one? Okay. Yes, Kirti, your third answer is correct. Very good. So the third answer, you can see directly, third part's answer is that at t equal to t by 2, the velocity becomes purely horizontal. So that time, becomes like this. Or you can also understand it this way, that when v is horizontal, the y component should become 0. So the y component is u sine theta minus gt. That is okay, people. So this is an example of various types of calculations that are done. The standard case of projectile motion. Now, next thing we will take a look at is the equation of trajectory and its application. So look at a couple of application examples of equation of trajectory also. So before that, let's start with the equation of trajectory itself. So taking our standard reference frame, x-axis horizontal, y-axis vertical, and the origin is the point from which we have projected the particle at time t equal to 0. So if it follows a path like this, then we already know how to write the coordinates and the velocity at time t. So we have the equation that x is equal to u cos theta t and y is equal to u sin theta t minus half gt square. So this represents the position as a function of time. Now from this only we generate the equation of trajectory. So if we eliminate time between the two equations, we get a relation between x and y. So that relation, it represents the equation of trajectory. So by doing this operation, that from this first term, we can take t as x upon u cos theta. And now we substitute in the second equation. So y becomes u sin theta into t. Okay, so we get the relation that y is equal to x tan theta minus half gx square upon u square cos square theta. So this equation actually becomes our equation of trajectory. So this basically means that every point xy that lies on the path or trajectory, trajectory is just another word for path, satisfies this equation. That is the meaning of this. Okay. Every point that lies over here, all the points that constitute the path through which this particle has gone through, they satisfy this equation. So now in this, you can see that y is a quadratic function of x. So that basically implies that the path or trajectory is a parabola. The shape of the path, it is not a semicircle or an ellipse or something like that. It is precisely a parabola. Yes, that's very good. Okay. So just make a quick note up to here, then we will understand some more aspects about this equation of trajectory, and then we'll look into typical types of numerical problems where we can apply this directly. Okay, so now the other thing to notice about this equation of trajectory is that it's of the form y is equal to some constant into x minus some constant into x square. This is the form of the equation, okay, where a and b are constants. Okay. A is equal to tan theta, where theta is the angle of projection, and b is equal to half g upon u square cos square theta. So now within this we can understand one more thing. We can also, the equation can be expressed in terms of the angle of projection and the range, horizontal range. Okay. This is a very useful way of writing the equation by doing this. That in this original equation, what we'll do is we will take x tan theta common. So the first term becomes 1 inside the bracket. The second term becomes, now I've taken x common outside, so x square becomes x. And I've also taken tan theta common. So I'll have to divide this by tan theta. So I have to take one tan theta in the denominator. So now you can see that this term g upon 2u square cos square theta into tan theta is the same thing as g upon 2 u square sin theta cos theta, which is g upon u square sin 2 theta, which is 1 by r. Okay. So ultimately, you can see that we can also express the equation of trajectory in a very useful form like this. This is the same thing as the above equation, but it's just written in a different way. It's written in terms of r and theta. Okay. So this is another form of the equation of trajectory, where of course we know the formula for r is u square sin 2 theta by g. Okay. So this is a very useful way of writing the equation of trajectory when it comes to solving numerical problems based on it. Okay. Whenever we are applying the equation of trajectory, it's usually, I'm saying, it's more useful to write it in this form rather than write it in the above form, x tan theta minus half gx square upon u square cos square theta. It's ultimately one and the same thing, both of them, but it's much more useful. And I will next we will work on some problems based on that, where we'll demonstrate how this second form of the equation of trajectory can make problem solving much faster for certain type of problems.
So here x and y are the different coordinates which are different intervals of time, right?
Yes. So basically, now if you are to trace the path of the particle starting from t equal to 0 till capital T when it lands, at every different instant there are different values of x and y. Those are the positions at the different times. But each of those positions, each of those coordinates x comma y, this satisfies this equation. That's why this is called the equation of trajectory.
Okay, sir.
Okay, so if we actually plot this accurately on a graph paper, that plot or that curve represents the actual path along which the particle is moving. It would have gone through each and every point on that curve at some point of time or the other.
Okay, sir.
Okay, so now let's see some application examples. So there are certain types of problems which become extremely easy to solve if we use equation of trajectory. So I'm going to try to stick to those kind of examples in the next few minutes. Okay. So suppose we have this situation, projectile is fired at t equal to 0 such that its range r is equal to, let us say, 240 meters, and the maximum height reached is h equal to, let us say, 45 meters. So we want to find the angle of projection theta. Okay, and we also want to find the height above the ground at an instant when the horizontal displacement is 180 meters. when it is covered a horizontal displacement of 180 meters, we want to find out what is the uh, height above the ground. Okay. So first of all, let's visualize the problem. Then we will see how we can make use of equation of trajectory to really simplify the question. I'll also show you that if we don't use equation of trajectory, then from the standard formulae or equations, how we can still come to the answer, but it will be that much more complicated. So at t equal to 0, we're projecting it like this. Now the things given to us here is that the range is 240 meters and the maximum height it is reaching is 45 meters. And from that, the two things we have been asked to find out is what is the angle of projection. Okay. And the other thing is at some instant of time, when the x coordinate has become 180 meters, the horizontal displacement, we have to find what the height from the ground is. Second is when x is equal to 180, what is the value of y? That is what we have to find. Okay. So you can see that first method I'll go for is the equation of trajectory method. Okay. So y is equal to x tan theta into 1 minus x by r. Now in this I know that r is 240, but theta I don't know how much it is. Okay. But I also have the information that this is 45 meters given. Okay. Now I know that when x is equal to r by 2, at that instant y becomes h. That is the maximum height position. Okay. Know that when it reaches this position here, at this position only x is equal to r by 2, y is equal to h. So substitute this information in the equation of trajectory. So I have the y coordinate is h when the x coordinate is how much? R by 2. So I have this very interesting relation that h becomes r tan theta by 4. Okay. So here that means that 45 should be equal to 240 by 4 times tan theta. So from this now I can find out the value of theta. Okay. So you can see that it's quite easy solving it this way. I don't have to write 2 or 3 different equations and compare them and all that. So just find out the value of theta from this paper. Yes, that's correct, Kirti. Very good. So you can move on to the second part of the question, Kirti, now. Yes, Anirudh, that's correct. Very good. Okay, so very good. Number of people have worked this out. 11.25 is the correct answer for the second part also. So let's complete this calculation. So we can see from here that next step, tan theta will become 45 by 60 or 3 by 4. So that means theta is equal to tan inverse 3 by 4 or 37 degrees. So 37 degrees is our angle of projection. This is the first part's answer. Okay. Now for the second part, what we can directly do is we can see that y will now become 3 by 4 x into 1 minus x by 240. Okay, this is the equation of trajectory because we have substituted tan theta equal to tan 37 equal to 3 by 4 and r equal to 240. So now we want to find y when x is equal to 180 meters. We just have to substitute this over here. It becomes a single line solution. See, just substitute this here. So 3 by 4 into 180 into 1 minus 3 by 4. So this should be the y point. Just have to check the calculation once more. Preeti, just check your calculation once more, but Anirudh, your answer is correct. Very good. So basically, this is the shape of the path. This is 240. 45 meters. So at this point, this is what will happen. This is 180, and this is apparently 33.75. So this is the height from the ground. When x is equal to 180 meters. Okay, now see, if you had gone with the standard formula based method instead of this, same problem by standard formulae or equation method, then what we would have done in this question is that given r is equal to 240 meters, you would have said that okay, u square sine 2 theta by g is 240 and h is equal to 45 meters. So u square sine square theta by 2g is equal to 45 meters. That's your second equation. Okay. Now you can do this operation, divide equation 2 by equation 1. So you'll get sine square theta by 2 times sine 2 theta is 45 by 240. So sine square theta divided by 2 times 2 sine theta cos theta would have been so this is how much now 45 by 240 plus divided by 3 by 5 16. So you would have seen that tan theta is 3 by 4. So theta is 37 degrees. That's the first thing. Okay. Then what we would have done is from either of the two equations, for example, from equation 2, u square into 3 by 5 whole square by 20 is equal to 45. So from this, you would have found out how much u is. So that for the second part, we have that x is equal to u cos theta into t. So for x equal to 180 meters, we can find the value of time, and then y is equal to u sine theta t minus half gt square. We can substitute this value of time here, and you can find the value of y. But you can see this is quite a lengthy method. Okay, we're going by this. In comparison, it's quite a bit more lengthy than the usage of equation of trajectory, especially the second part, because you have to solve for time, substitute and all that. And before that, you have to find u also, okay, so that you can solve for time. So I think you will get u as 50 meters per second. Solve. When you substitute that here, you get 50 into cos theta, that is so time will be 4.5 seconds. So doing all that calculation. So you can immediately see the advantage of using the equation of trajectory method in a situation like this. So when you do the questions from H.C. Verma in your module, etc., for projectile motion, you will come across problems where you will be able to understand that if a question is not involving any calculation with respect to time, like this question, nothing with respect to time is given in the question, nothing is asked. It is only to do with the geometrical properties like range, maximum height, the coordinates at a certain time, etc., then you can always use equation of trajectory to give you a faster solution. Whereas anything which is time based, like the question we did earlier, you wanted to find the time when the velocities become at 45 degrees, those kind of things, you have to use the time based equations. That is the instantaneous coordinates and velocity as functions of time. So that's like a general guideline to solving these type of questions. Okay. Now we move on to the second aspect of projectile motion. So far we've seen the standard projectile motion, where projection is happening from a horizontal plane and the object projected is coming back to the same horizontal plane. Now we look at the second part of projectile motion, where the projection is done from a heighted point or from a height above the ground. So projection from a height, that too in this we'll see the first case as horizontal projection from a height. So the situation here is, let's say something like this. So let's say this height is capital H, and from that position here, we are projecting an object horizontally at time t equal to 0. So once we project it, and again it's under the action of gravity, we have this kind of a path to strike the ground. Okay, Rohan, I'll go back to the previous section again. So now this is the so-called horizontal range it's covering, and it impacts the ground at some time t with an impact velocity like this. So the idea is that given the value of u and h, you want to find capital T, R, and impact speed. Okay. And in general, the displacement and velocity as functions of time. So this is what we understand about this case. All right, so I'll just go back to the previous section once more. Just let me know when you've completed going through it, Ron, and we'll come back to this. So the equation of trajectory method was clear, na? The one before this. So I'm assuming that one was clear. Now going through the standard method from the standard formulae instead of equation of trajectory. This was the second method of solving. Okay. So while this is a more standard method, but this is lengthy.
Yes, sir. The screenshot. Sir,
Okay, so let's move back to this part. So now here, to solve this situation, horizontal projection from a heighted point, what we'll do is, once again, we'll take the origin of our reference frame at the point of projection. Okay, but this time we can take the y-axis downwards, because you can see the object is straight away going downwards. It's not first ascending and descending. So it will be more convenient to take the y-axis in the downward direction. So we can take our reference frame like this. That this horizontal direction is our x-axis. The vertically downward direction is our y-axis. More convenient here. Okay. And the origin is the point of projection. So with this now we can write our initial velocity as ui cap and our acceleration as gj cap, because we've taken the downward direction as positive. So ux is u, uy is 0, whereas acceleration's x component is 0, acceleration's y component is g downward. So at some time t, the particle reaches here, coordinates are x, y, and the velocity is v. So you can see that at time t, in general, the x coordinate will become ut. Okay, from this two you can see, whereas the y coordinate will become half gt square. From these two you can see, and the velocity would have become u I cap plus gt j cap, because the horizontal component of velocity will remain constant, whereas the vertical component will be gt. So from this you can see. Okay, so this is at the instant time t, position and velocity. So now from this you can see the next thing, that at the time when it hits the ground at t equal to capital T, the impact with the ground. First of all, what is happening at this time? The y coordinate is becoming h. You can see it's, so from this equation, so from equation 2, you can see h is equal to half gt square. So the time taken is square root of 2h by g to reach the ground. Then from equation 1, x is equal to r. Okay. So second thing, and similarly from equation 3, we will find the impact velocity. So when it impacts the ground, it will have a vertically downward component of root 2 gh, and the horizontal component u that remains constant throughout. So next we'll take a numerical example based on this, but first just make sure you understand first of all the equations, and from those equations how we generate the standard formula. Okay, so let's look at a numerical example.
Sir,
Yes,
sir, in this case, what will be the angle with which angle of the impact velocity with respect to the ground?
that we can find from the vector. If we know the components, no, we can use that tan theta formula for the components for any vector.
Okay, sir.
Understood? So let's do a numerical problem. In that we'll calculate that also, the angle of impact. So suppose this is what is happening from a certain height. Now let's take this height to be 320 meters. So at t equal to 0, we are horizontally kicking off an object at a speed of 60 meters per second. So it comes and hits the ground like this. Some time t with an impact velocity, let's say bi, which is also now making this angle here. So this angle with the ground, and at a range like this. The horizontal displacement. So given all these things, u is 60 meters per second. The height of the position from which we are throwing it is this much, and g is 10 meters per second square. First of all, we have to find the time, the range, and the impact speed vi. We have to also find the angle of impact, that is the angle theta of the impact velocity with respect to the horizontal surface. And let's add one more part to this, to also find displacement and velocity at t equal to 6 seconds. So just work this question out. It involves all the aspects of calculations related to this case. Okay, so I'm just first of all giving you the answers, then you can verify them yourself and we'll discuss. So you should be getting time as 8 seconds, the range as 480 meters, and the impact speed will come 100 meters per second, but it will be at an angle of 53 degrees with respect to the horizontal. So first of all, just verify these answers. Yes, Anirudh, Kirti, very good. You got this correct. Okay. Now the second part, at t equal to 6 seconds, you will see that the velocity will become 60 horizontal and 60 vertical. Or magnitude of v would have become 60 root 2. And the x coordinate, when you calculate, is 360 meters. The y coordinate is 180 meters. So the displacement would have been 360 I cap plus 180 j cap in meters. But remember that this j cap is taking the y axis as downwards. So once again, the standard method, you take the horizontal as your x-axis, vertically downward as your y-axis. So you can see that you can apply this formula directly. Okay. So the impact velocity will be so this is the first part of the question. Now the second part is where you understand that this impact velocity being 60 I cap plus 80 j cap. It's like this, where this component is 60 and this component is 80. So this angle theta now is such that that's the second part. Okay, and for the third part, just have standard situation that at any time t, the x coordinate is ut, the y coordinate is half gt square. Okay, so therefore, just by calculation, you will get this. Okay, people, so hope this is clear. So with this, we conclude today's session. In the next class, we will look at the situation of oblique projection from a height. Okay, so we'll look at this kind of situation, that from a point like this, we project at u, which is at an angle theta with respect to the horizontal, and how it will go on a path like this before finally hitting the ground some time t. So we look at this kind of situation, and then after that we will look at more problems and applications of projectile motion before moving on to the final part of kinematics after that, which will be relative motion. So till then, please continue working on the problems from straight line motion as well as projectile motion from HC Verma as well as your module. Plus the worksheet I've sent you, I'll be sending you another worksheet for projectile motion also. So that's it for today's session, people. Wish you all the best. Have a nice day. Thanks for attending.
Sir,
Yes.
so can you show the previous slide for a minute, this?
Yeah.
Yes, sir, I took the screenshot.
Thank you, sir.
Thank you, sir. Thank you, sir.